Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss use of Laplace transform to simple electrical circuits. The electrical circuits like RL circuit, RC circuit and LCR circuit. Let's begin. First, RL circuit. Let we consider an electrical circuit that consists of a resistor having resistance R. We provide an voltage source EMF E and an inductor having inductance L and a switch S. So, the applied EMF is dropped across the resistance R and inductor L. From that of equation of EMF, here the potential drop is IR, current into resistance. Here the potential drop L into di by dt. So, the applied EMF E, in case of inductor we have L di by dt plus in case of resistor I into R is equal to E. Our task is to calculate I. Let me take the Laplace transform on both sides. Taking Laplace transform to both sides, the constant is L. From the definition of derivative of Laplace transform, we have that is S I bar minus I at 0 plus R into I bar is equal to Laplace transform of E. From the definition of Laplace transform, that is 0 to infinity e to the power minus st e dt. So, Laplace transform of di by dt is equal to s I bar minus I at 0, and Laplace transform of IR, as R is the constant and I as I bar, and Laplace transform of E from the definition of Laplace transform, which implies L S I bar I at 0 means current at t is equal to 0. Here we have I is equal to 0 when time t is equal to 0. There will be no such current throughout that of circuit when time is equal to 0, plus R I bar is equal to integration from 0 to infinity e to the power minus st e dt. Taking I bar as common, Ls plus R is equal to integration from 0 to infinity e to the power minus st e dt. Equation number 2. There will be a condition. What is the condition? If the switch is disconnected, means after time let t is equal to a, what will be the condition? There will be a condition is applied to that of electrical circuit containing R and L, but if the switch is disconnected at time t is equal to a, then that EMF has E when that t in between 0 to a, and that EMF will be 0 when that time is greater than a. That will be the condition for EMF to that simple electrical circuit having resistor and inductor. So, the equation 2 now changed to the limit 0 to infinity as 0 to a and a to infinity. Therefore, equation 2 becomes I bar Ls plus R is equal to integration from 0 to a e to the power minus st e dt plus integration from a to infinity a to infinity e to the power minus st e dt. At a to infinity, that value will be 0. So, that integral is 0. Therefore, we have I bar Ls plus R is equal to E as constant, its integration results e to the power minus st divided by minus s using the limit from 0 to a. We have E divided by s 1 minus e to the power minus as, that is equal to e by s minus e by s to e to the power minus as. Therefore, I bar is equal to that Ls plus R is divided. We have E divided by S whole into Ls plus R minus E divided by E into e to the power minus as divided by s whole into Ls plus R. Equation number 3. That type of equation can be solved. We have the value of I, so we have to take the inverse Laplace transform here. taking the inverse Laplace transform we get I, taking the inverse Laplace transform on both sides, we have inverse Laplace transform of I bar is equal to I, inverse Laplace transform ILT, E divided by S whole into Ls plus R minus inverse Laplace transform e to the power minus as divided by s whole into Ls plus R. Instead of L to the power minus 1 as inverse Laplace transform, why we write ILT, as there will be the terms as L as the coefficient of self inductance. Therefore, we write ILT, where ILT referred as inverse Laplace transform. Took it as equation number 4. Now, we have to found what is the inverse Laplace transform of this and inverse Laplace transform of that. Therefore, what is the inverse Laplace transform of E divided by S whole into Ls plus R is equal to inverse Laplace transform E divided by, here Ls as common, so S plus R by L, which is equal to inverse Laplace transform of E by L, that L is divided to that of numerator, sorry, to that of E. So, S whole into S plus R by L E by L is constant, E by L to outside. So, inverse Laplace transform 1 divided by S whole into S plus R by L, 1 divided by S whole into S plus R by L can be written as inverse Laplace transform, that bracket term is written as L by R whole into 1 by S minus 1 divided by S plus R by L. When we take the LCM and multiplying to that of term L by R, we have that particular term 1 divided by S whole into S plus R by L. So, L by R is a constant, E by L into L by R. So, inverse Laplace transform 1 by S minus 1 divided by S plus R by L. L cancel out, E by R. So, inverse Laplace transform of that kind of expression 1 minus e to the power minus RT by L. And equation number 5. Next, we have to calculate the inverse Laplace transform of this one. To calculate the inverse Laplace transform of that one, again inverse Laplace transform e to the power e into e to the power minus as divided by s whole into ls plus r. Same term, that term is very similar to this term, but e to the power minus as is multiplied. Here we use some properties of Laplace transform. As you know, from the second shifting property, that is, if Laplace transform of the function f of t is equal to f of s, then Laplace transform of f of t minus a into u of t minus a is equal to e to the power minus as f of s. That is the second shifting property in Laplace transform. That is why we have the inverse Laplace transform in similar pattern. Inverse Laplace transform of e to the power minus s f of s will be that function as f of t minus a into u of t minus a. Look at expression. Here we just add e to the power minus as, e to the power minus as to the previous equation as inverse Laplace transform of e divided by s whole into ls plus r is equal to that much. So, from that expression, the inverse Laplace transform of e to the power minus as f of s is equal to f of t minus a into u of t minus a, u of t minus a as the unit step function. So, the inverse Laplace transform is equal to e by r 1 minus e to the power minus r by l t minus a, as it will be f of t minus a into u of t minus a. Okay, that property is used here to evaluate the inverse Laplace transform of that particular term. We have choose it as equation number 6. From equation number 5 and equation number 6, these two values are put in equation number 4 to calculate I. Then using equation 5 and 6 in equation number 4, we obtain I is equal to e by r, its inverse Laplace transform e by r whole into 1 minus e to the power minus r t by l, 1 minus e to the power minus r t by l plus e by r, its value 1 minus e to the power minus r by l t minus a u of t minus a, and equation number 7. Here use the property of unit step function. As we know, the value of unit step function, but for the value of t when in between 0 to a, then the unit step function is equal to 0. Therefore, equation 7 reduces to I is equal to e by r 1 minus e to the power, in place of that term cancelled out, only that term exists, e to the power minus RT divided by L. Equation number 8. Similarly, but when t is greater than a, so the unit step function is equal to 1, as we have two conditions, when the value of t in between 0 to a and when the value of t is greater than a. We prefer two conditions for that of EMF. So, the equation 7 reduce to the form, therefore, equation 7 reduces to I is equal to e by r 1 minus e to the power minus RT by L minus e by r look here, that is the minus term, as that one is the minus, there is the minus. So, e by r 1 minus e to the power minus r by L t minus a, e by r taking common 1 minus e to the power minus r t minus a divided by L minus e to the power minus r t by L. Therefore, e by r e to the power minus r t by L as common in these two sides. We have e to the power minus r a by L minus 1, that be the expression for I when t is greater than a. In this way, by using Laplace transform, we calculate the current in RL circuit. First we take the circuit, then equation of EMF applied to that of circuit, taking Laplace transform and condition for EMF, then inverse Laplace transform of these two terms, inverse Laplace transform of these two terms are evaluated, then the values are putted and two conditions are applied for unit step function. We have the expression for current for RL circuit. Next, for RC circuit, let we consider resistor and a capacitor is connected. Resistor having resistance R and capacitor having capacitance C, and source of EMF is applied, and that E of t EMF is expressed as E naught u a at t minus u b at t. E of t E naught u a at t minus u b at t. U a at t and u b at t are the unit step functions. This is the notation to write unit step function. So, the equation of the EMF in that circuit, here the potential drop I into R, at capacitor the potential drop Q by C, the applied EMF E as a function of t. Here we have E as a function of t is equal to E naught u at A, u at B. What is u at A? U at A is equal to u of t minus A, and u at B u of t minus B. These two are known as unit step function, unit step functions, and the value of u of t minus A is equal to 0 when t less than A, and that value will be 1 when t greater than equal to A. Similarly, for u of t minus B is equal to 0 when t less than B and is equal to 1 when t greater than equal to B. And but the charge is the integration over the time 0 to t, current as a function of time, let tau be the time, d tau. These are some basics for that of RC circuit. These values are put here, or we have IR plus 1 by C in place of Q, integration from 0 to t I as a function of time is equal to E naught u a of t minus u b of t. Let equation number 1, that one be equation number 2. Now, we apply the Laplace transform of that equation, taking Laplace transform of equation 2, we get R as constant. Here we take Laplace transform LT, as there will be the sum of the terms like L and T. So, instead of writing only L, we just write LT as Laplace transform of I plus 1 by C Laplace transform of the integral 0 to t I d tau is equal to Laplace transform of u e naught u a at t minus e naught u b at t. So, R Laplace transform of I bar plus 1 by c Laplace transform of that integral. Using the integration of Laplace transform, we have I bar divided by s is equal to e naught its Laplace transform e to the power minus as e to the power minus bs. Laplace transform of unit step function. Formula is used here. Therefore, I as common, r plus 1 divided by cs I bar is equal to e naught by s e to the power minus as e to the power minus bs. Therefore, I bar is equal to the term divided to this side. So, e naught divided by s whole into r plus 1 divided by cs e to the power minus as minus e to the power minus bs is equal to that s is multiplied within that of bracket. So, we have e naught divided by s r plus 1 by c e to the power minus as minus e to the power minus bs. R taking common, so e naught r as common, so s plus 1 by r c e to the power minus as minus e to the power minus bs. We have that r is divided, so e naught by r divided by s plus 1 by r c is equal to e to the power minus as minus e to the power minus bs. Equation number 3. For that term, let us substitute let us substitute e naught by r divided by s plus 1 by r c is equal to f. Therefore, we have I bar is equal to f whole into e to the power minus as minus f whole into e to the power minus bs, and its Laplace transform, its inverse Laplace transform of f is equal to inverse Laplace transform of e naught by r divided by s plus 1 divided by r c. We have e naught by r, so inverse Laplace transform 1 divided by s plus 1 by r c is equal to e naught by r e to the power minus t by r c as the inverse Laplace transform of 1 divided by s minus a is equal to e to the power 80. That formula is used here. Taking the inverse Laplace transform, taking inverse Laplace transform on both sides, so I is equal to its inverse Laplace transform as inverse Laplace transform of f e to the power minus as minus inverse Laplace transform f e to the power minus bs, which is equal to, as we have E naught by R e to the power, that is minus e to the power t by a, t minus a divided by RC into u of t minus a minus e to the power minus t minus b divided by RC into u to the power u into u of t minus b. Here RC, the term R into C is known as time constant for the circuit. R into C is the time constant for circuit. So same concept is used if t is less than a and less than b, then the current I is equal to 0 in the circuit, and but if t is less than a and less than b, so I is equal to E naught divided by R e to the power minus t minus a divided by RC. So the current I, as we write it, therefore I will be E naught divided by R e to the power minus t by RC into e to the power a divided by RC. Or I is equal to E1 e to the power minus t by RC, where we take E1 is equal to E naught by R e to the power a by RC. By using that expression and putting that value, we have the required expression for current for RC circuit by using Laplace transform concept. Next, for LCR circuit, what will be the current? Let we refer a resistor, an inductor and a capacitor connected in series having EMF E, and let we take the impulsive voltage is applied to that of circuit. Impulsive voltage, which one is E into del t, that is the time. The voltage equation will be, here the potential drop I into R, at inductor having inductance L, the potential drop L di by dt, capacitor having capacitance C, here the potential drop Q by C, applied EMF E del t, or I R plus L di by dt plus 1 by C integration from 0 to time t I di E del t. This is I dt, I dt. I is a function of t. And equation number 1. Taking Laplace transform on both sides to evaluate the value of I. Taking Laplace transform on both sides, we have the Laplace transform of IR is equal R as constant for I, that will be I bar, plus L Laplace transform of di by dt, derivative of Laplace transform as S I bar minus I at 0 plus 1 by Laplace transform of integration concept is used as Cs I bar is equal to Laplace transform of E del t as E. So, I at 0 at initial time t is equal to 0, I at 0 is equal to 0. We have R I bar plus L S I bar plus I bar divided by Cs is equal to E, or L I bar as common. We have we have 1 divided by one, that is R divided by L plus S plus 1 divided by LCS is equal to E, or again 1 by S taking common. So, L by S I bar RL into S plus S square plus 1 divided by LC is equal to E, or I bar S square R by L into S, R by L into S plus S square 1 by LC is equal to E S by L, that L by S is multiplied here, and equation number 2. Here let us substitute R by L is equal to 2A, 1 by LC is equal to A square plus B square, or we have I bar R by L as 2AS plus S square plus A square plus B square is equal to E by L into S. Therefore, I bar is equal to E by L S divided by, write it as S square plus 2AS plus A square plus B square, that is written as E by L as S plus A minus A, there will be no such change, divided by, that will be the square of S plus A square, S square plus 2S plus A square plus B square, or I bar is equal to E by L S plus A divided by S plus A square plus B square minus A divided by S plus A square plus B square. Now to achieve I, we have to prefer inverse Laplace transform here. Taking inverse Laplace transform, we get I is equal to E by L inverse Laplace transform of S plus A divided by S plus A square plus B square minus inverse Laplace transform A divided by S plus A square plus B square. Or I is equal to E by L inverse Laplace transform of that kind of function as e to the power minus a t cos bt minus here a by b e to the power minus a t sin bt. That is the required expression for current in case of LCR circuit. By taking LCR circuit and using Laplace transform, we evaluate the mathematical expression for current. So, with the help of this video lecture, we can understand the use of Laplace transform to simple electrical circuit. First, RL circuit, and that be the expression for current. Next, RC circuit, finally that be the expression for current, and LCR circuit, expression for current. So, with this useful and informative notes, let me wind up this session. Thank you.